Hello guys, today we are going to solve problem C and D from Codeforces Educational Binary Search Step 2. If you haven't watched Pascal's video lectures, I'd strongly recommend watching them first, then solve problem A and B because these problems are basically optimization problems that require discrete binary search. Now, just to give a brief about discrete binary search, so when we listen the term binary search, first thing that comes to mind is that there is a sorted array or vector. But in discrete binary search, the search space that is not necessarily a sorted array or a sorted vector, or it is also possible that the search space is not a container at all, like array or vector. It is just a monotonic range. It can be array. It doesn't need to be an array, and it can be continuous or discontinuous. So this search space means we know that whatever answer we are searching for, that lies in this monotonic range. And this search space, just because it's not an array and it's not something given to us, that we are talking a range in which our answer lies, so that's why we call it discrete binary search. And coming to optimization problems, so optimization problems means that these problems have many feasible solutions, and one of them is going to be an extrema that is required. So it's like a maximum or minimum. For example, we can look at this question: find the maximum number x such that x square plus x power 4 is less than equals to c. So here c can be any real number that you have to take as input. Now if you look at this question, in this question, what is the search space? So it's already given that c is greater than 1. So if I say that, let's say my x equals to 0, so I can always say my x square plus x power 4 is less than equals to c, because c is already greater than equals to 1. And if I take x equal to c, I can say c square plus c power 4 is greater than c, because both are positive, x square and x power 4. So I can safely assume that whatever is the answer of this question, it lies between 0 and c. So in this case, our search space is 0 and c. You can optimize search space more like c by k something. K can be any integer if you know their additional information is provided in the question. Okay, so now how to solve it using binary search? So now I claim that my search space is monotonic, which means like this function x square plus x power 4 that we want to calculate the value of, I'll say that this function is already an increasing function. So let's say if I say there is a x equals to x naught and x naught square plus x naught power 4 is less than equals to c, then I can say for all x less than x naught, x square plus x power 4 will be less than c, because it is a monotonic function. Similarly, if I say that there is a x equals to x naught such that x naught square plus x naught power 4 is greater than c, then for all x greater than that x naught, x square plus x power 4 will be greater than c. So the idea is to divide our range into our search space into different ranges. Like for 0 to x naught, we now know that okay, if x naught is a feasible solution, then everything less than x naught is also a feasible solution. And if x naught is not a feasible solution, everything greater than x naught is also can't be a feasible solution, because the function is monotonic. So the next step is to maintain a loop invariant. Loop invariant means for each iteration we are going to maintain, let's say, two pointers, let's say low and high, and so our range 0 to low is going to maintain all set of all feasible solutions, that is the green zone here you can see. And our low to high will be the unexplored search space. Initially our low to high is the entire search space, because we haven't started exploring the search space yet. And high, from high to the end range of the search space, is going to be the can be the feasible solution. So this is the condition that we are going to maintain after every iteration of that loop. That's why that's why it's called loop invariant. So what we're going to do is we are going to bring these two pointers as much as close as possible, because that's what because we know that our answer lies in this low pointer and high pointer. And even though we have already some feasible solutions, but they are, it's not I mean, we can't be sure that they are extreme solutions, right? So the idea is to bring these two pointers close together, and once they meet, since initially our low pointed to the optimal solution in each loop, we can return the low value at the end as our global maxima. So okay, and I'm not going to solve problem A and B because Pascal has already solved them in his lectures. So now let's jump to coding C and D. So let's solve C. Question is, this morning the jury decided to add one more very easy problem to the problem set of the Olympiad. The executive secretary of the organizing committee. Okay, so the question is that you have to make n copies. Initially you have only one copy of a question paper, and you have two copier machines, right? And one of them copies in x seconds and the other one is in y seconds. You can use either one or both at the same time, and once you have made one copy, then you don't need to only copy from the original question paper. You can use the new generated copies also. And the question asks that to find out what is the minimum time required to make n copies. Input is n, x and y. Output is minimum time in seconds required. Okay, so let's take input first. Okay, now to maintain the loop invariant here, the minimum time required, let's say we have two pointers, right? Low. So this low is like this low will point to a time in which making n copies is not possible at all. So I can say, like, initially my low is 0, because you see n is greater than 1, so in at least n will always be 1 or greater than 1, right? So in 0 time you can't make one copy. So let's take low equals to 0, and for high is like, basically, so you have two machines, one copies in x seconds and another copies in y seconds. So basically I can say that greedily I'll choose the machine that takes less time and make n copies using only that machine. So without any optimization, I can say my high will be time required to make n copies using minimum of x and y, like the machine which takes the minimum time, I'm going to use only that machine. Then we'll start binary search. So the idea now here is, I'm going to check, once I find this mid time, I'm going to check, is it possible to generate n copies in the mid time? If it's possible, then I can move my high pointer to mid time, because high always referred to the time in which it was actually possible to generate n copies. Right? So let's say I can write a function like is possible, which will take parameters like all n x y and this mid time. If it's possible, then my new value of I will be mid time. Else if it's not possible, then I'll shift my load to mid time. And at the end, I'll just return the high value, because my high value is in this loop invariant. My high value is the value that points to the time in which I can make n copies. Okay, so let's write the each possible function. Okay. So first of all, I can say one thing, that if my mid time is less than minimum of x and y, then I can say like, okay, so at least I need minimum of x and y time to make at least one more copy. And if mid time is already less than that minimum value, then we can't generate any copies, right? So let's say if mid time is less than false. Otherwise, what I'm going to do is, I had only one copy, and I'm going to make another copy using the machine that takes less time. This is like a greedy choice, because once I have two copies, I can use two machines. I can't use one copy in two machines simultaneously, so I need to generate one more copy at least. So I can say I can subtract time minus min equals to 1. Now I have two copies, right? And the time required to generate the second copy is already subtracted from mid time. So now I'm going to check, okay, I have two machines, one takes time x and one takes time y. So during this mid time, how many numbers of copies each of these machines are going to make? So and I'm going to say, okay, so during this mid time, my first machine that took x time made this much copies, and the machine that used to take y time made this much copies, and initially we made already one copy. So if my total number of copies is greater than equals to n, then it's possible to make n copies. So I'll say something like mid time by x plus mid by y plus 1, because I have already made one copy. This should be greater than equals to n. Yes. Three, let's see, okay, 3. Four. Okay, let's submit this. Okay, accepted. So let's solve problem D. In this question, the organizer want to inflate m balloons and he has n assistants. So n assistant are being used to inflate m balloons, and for each of the ith assistant they take time ti to inflate a balloon, and every time after they inflate z balloons they get tired and they rest for yi minutes. Okay, so and the question asks to find the time it takes for all the balloons to be inflated, and then the number of balloons inflated by each of the assistants. Okay, input is m n t z y. Okay, so let's cover the test case first. Now each assistant has this attribute t, z, y, so I'm going to create a custom structure of assistant. Let's call it ask. We need t, z and y. Okay, the array of assistant, and for each okay, now we have the array of assistant. Okay, now first thing we need to print is the minimum time that will be required to inflate all the balloons. Okay, so let's say if my time is like let's first define the search space. Like I can say in time like -1 I can't inflate any balloons, right? Because m can be 0, so time 0 is possible, but in -1 I can't inflate any balloon. Similarly, the maximum time I'm going to require I can take this any big value like okay. Now to maintain loop invariant, now I'm going to check if it is possible for these n assistants to inflate m balloons in this time or not. If it's possible, then I'm going to move my max time pointer to this time, otherwise my min time pointer will be moved. Okay, so I need to pass array size, number of balloons, and then this time. If it's possible, then my max time will be time, else min time will be time. At the end I'll return max time. Okay, so now let's write this function is possible. So initially total balloons that are inflated is 0, so let's take a variable total balloons. Now for each of the n assistant, let's take t or y indirectly the corresponding values like okay. Now I need to know how many balloons within this time this particular ith assistant can inflate. So this is going to be another discrete binary search here, because they either can make 0 or they can, I mean, we don't know the search space here exactly, but let's assume like low equals to 0 and high equals to. So this low and high value here is like, I'm going to start checking from 0. Is it possible to inflate 0 balloons, or is it possible to inflate 10 power 9 balloons within this time, and whatever is the optimized answer, I'm going to add it to the total balloons. So while high is greater than location. So this low and high here actually points to number of balloons here. Let's say balloons low plus high. Now if it's possible to, for this particular assistant to inflate these balloons, number of balloons in this time, then I am going to move my low pointer to this balloon, because at any time you can inflate 0 balloons, you don't need time to inflate 0 balloons. So you can say like it's possible. That's going to be another function. This function will take parameter t, z, y, this exact number of balloons and time. If it's possible, then my low will be this value, else value. And once I come out of the loop, my low pointer will have the value that this particular assistant can inflate. So that's what I'm going to add to total balloons. And at the end, I'm going to return for now the total balloons has the value stored, then how many number of balloons all of my n assistants can inflate in this time. So I just need to check that whether this total balloons is greater than equals to m or not. If it says, then it's possible. Now let's write this function. It's possible for a particular assistant to inflate this amount of balloons or not. Okay. Now, if you look at the question, we see that the ith assistant takes t time to inflate one balloon, and every time after zi balloons, they get tired, right? So let's say for one batch of zi balloons, they'll take ti into zi time to inflate the balloons, then they'll get tired, so then they'll take extra y minutes to rest, right? So I can say for each batch of zi balloons, let's call this batch time balloons, the time this assistant will require will be z into t plus y. Now how many such batches will be there? So number of batches will be the total number of balloons that he is going to inflate divided by and in each batch divided by z, because in each batch he is going to inflate z balloons, right? Okay. Now the one more thing to notice here is it's written that if the assistant has inflated the balloon and needs rest, but he will not have to inflate more balloons, then it is considered that he finished the work immediately after the end of the last balloon inflation, not after the rest. Which means if a assistant each on his last batch, then after finishing his last batch we are going to take that time, and we are not going to add the time he is going to use to rest after the last batch, right? So how we are going to know that, like, is it the last batch or not? Because this is an integer division, right? And balloons by z might not always be an perfect, when it will be an integer, but balloons might not be perfectly divisible by z. So let's take a boolean variable okay to know whether this number of batches are last batches or not. If it's 0, then yes, it's the last batch, otherwise not. Now let's say that total time that this assistant requires, let's say let's call it current time. You said it's 0. If the last batch is counted in this number of batches, then I am going to subtract 1 batches, because for the last batch I don't need to consider the resting time. So my total time required will be batch time into number of batches plus, for the last batch, in the last batch I'll have z balloons, then I'll take t time for each balloon. Else if the last batch is not included, then my current time is going to be the time I'm going to need for finishing these batches plus how many balloons are left. Now the number of balloons that are left will be balloons mod z, and for each of these balloons I'm going to take t time. Yes, and once we have the total time required, we are just going to return a check whether this value is less than equals to time or not, because if it's less than equal to time, then it's possible for the particular ith assistant to inflate this number of balloons. Okay, so let's see, time required is yes, you already got the one. Now we have to print the number of balloons inflated by each of the invited assistants, and if there are several optimal answers, output any of them. Okay, so now uh, let's create an array to keep track of how many number of balloons all this each of these assistants can inflate within this interval max time. Let's call this count n. Initially all of the numbers are 0, 0, size of count. Now for each of the assistants, we are going to store what is the maximum number of balloons this assistant can inflate within this time, max time, t, z, y, and max time. Okay, so let's write this function. Okay, we are going to do almost similar thing here. So batch time is going to be z, t plus y, and so let's first count that how many number of batches will be there in this time. Let's call this batch count. Max time divided by batch time, and let's say we have some time remaining after finishing few batches. Let's call this remaining time, rem time. And initially total number of balloons is 0. So for this amount of batches, these number of batches, in each batch I am going to inflate Z balloons. So I'll directly add total balloons plus equals to this batch count into Z. Now if I have time left, then I'll check. First thing I'll check that since the ith assistant take t time to inflate one balloon, I'll check is it possible to inflate Z balloons or not anymore. So let's say like if remaining time by time taken for each inflation is greater than or equals to Z, then I can say okay, because I have still that much time left, I can inflate Z more balloons. Else I'm going to say else this remaining time is going to be the time for my last batch, right? So I'll just add remaining time divided by t, and I'll return total number of balloons. Okay, now once I have the values in count array, and these values are like what is the maximum number of balloons that each assistant can inflate within this value max time, and it's written that if there are several optimal answers you can output any of them. So I'm going to just greedily distribute them so let's say total balloons inflated equals to 0 initially. So what I'm going to do is I'm going to iterate over all the assistants. If already total number of balloons are not m, if it's less than equals to m, let's say if total balloons plus this count I each less than equals to m, then I can give this max time to this assistant, and I can tell him to uh, inflate maximum number of balloons that he can in this time, right? So I'm going to output this value. Else what I'm going to do is, if I have already inflated m balloons, so if my balloon count is already m, then this assistant need not inflate any more balloons, so we'll just inflate 0 balloons. Else this, let's say this else will be like, I need to inflate 3 balloons more, because that will get me to m balloons, but this assistant can inflate like something more than 3, which I don't need, right? So I'm going to output only the number of balloons that are required. And I'm going to set my total balloons equals to m. Okay, that's it. Let's see. Okay, let's submit this. Accepted. Okay.